AP Physics 1 Workbook, Unit 4, Work and Energy, Activity O, Conservation of Energy and Circular Motion. Please remember to pause or rewind the video as necessary. Read the scenario along with me, please. Engineers A, B, and C are responsible for creating a new roller coaster ride. Engineer A comes up with a idea sketched to the right, which is a solar system themed coaster. The track starts at point P at the top of a sphere, radius R, representing Jupiter, and then goes down a level and then goes over a sphere, radius little r, representing Neptune, the top of which is point Q, and then back to the ground again. The spheres are intended to be built to the actual scale of the planets they represent. The coaster consists of a single cart of mass m that experiences no friction or other dissipative forces. The coaster starts from rest at the top of point P. Two other engineers are extremely concerned about the safety of this coaster. If the normal force becomes anything other than zero, the cart loses contact with the track and the cart becomes a projectile, severely injuring the occupants. The engineers reason this way. Engineer B says, if the height difference between the top of Jupiter, so right here, and the top of Neptune is too much, the cart will be going too fast at point P, right, and will lose contact with the track. Engineer C says, no, it's not the difference in the height that's the problem, but it's the small radius of curvature in the track that in other words, the small r. Well, let's examine what's going on here. If we look at the energy at point P, the kinetic energy at P will be 0. The gravitational potential energy at P will be mg h. But now h, the height that you're falling right here, is radius and radius, which is m times g times 2r, or 2 mgr. At the top of Neptune, which we'll call point Q, the energy at the point Q, so we have kinetic energy at point Q, so I'm going to write 1/2 mv squared. You know you have kinetic energy because you're moving fast over the top. But you also have a little height above the ground as well, so you're still going to have gravitational potential energy at point Q as well. But this one's going to be mgh, where h this time is little r plus little r, or m times g times 2 little r, or 2 mg little r. I'm not including spring energy in this problem, as you can clearly see there is no spring. So to summarize this, in part A1, the speed of the cart when it's on top of the Neptune sphere, the system consists of the cart and the Earth. So at the top of Jupiter Hill, the energy is just all gravitational potential energy. At the top of the second Neptune Hill, the cart-Earth system will have gravitational potential energy, and this time the cart will also have kinetic energy too. Let's derive the scenario. We're going to write about it over to the right, and we'll derive it over to the left. The energy at the top of Jupiter and the energy at the top of Neptune are equal. So I'm going to call that energy J and energy N are equal. This is because there are no external forces doing work on the system. Remember, there was no friction or other dissipative forces. There was no external applied force. Nothing extra going on, right? So the gravitational potential energy of the cart is mgh, where each diameter of the planet is going to be 2 times the radius. Solving for the speed we get, well, first of all, let's go ahead and keep deriving this. So at the very top of Jupiter, we have nothing but gravitational potential energy. Okay, I'm going to call that initial. equals, now at the top of Neptune, you have kinetic energy final and you have gravitational potential energy final. Well, this would be mgh of Jupiter equals 1/2 mv squared plus mgh of Neptune. Now, we already established what this is. We already wrote that earlier. That's going to be 2 mg big R, because remember, 2 times Jupiter's radius was the height, equals 1/2 mv squared plus 2 mg little r, where 2 times the little r was the height that you fall from the top of Neptune's curve. So now we need to solve this equation for V. In order to do that, I'm going to go ahead and start subtracting this over to this side. And we get 2 mg big R minus 2 mg little r equals 1/2 mv squared. I'm going to multiply by 2 each term. I'm going to divide by mass each term. You can see mass is going to cancel. And then finally, I will square root. So V is equal to the square root of 4gr minus 4g little r. Now you can see 4g is common to both. So 4 times g and then times the quantity big R minus little r. The square root of 4 is 2. So we can pop that out, and 2 times the square root of g times the quantity big R minus little r. Part A2, the normal force of the cart when it's on top of the Neptune sphere. So now we're looking at centripetal force, okay? So let's see what's going on here. The top of the Neptune sphere, you've got the weight going down, and you've got the normal force going up. Now, going down is actually the causing force, because you can see that's pointing towards the center of the circle. You can see the normal force is not just going up, it's pointing away from the center of the circle. That makes this the opposing force. So if we looked at this, we're looking at Newton's second law, net force equals mv squared over r, net centripetal force. Now the net centripetal force will be mg to the center of the circle minus normal force equals mv squared over r. I'm going to add normal force and subtract mv squared over r, and so normal force is equal to mg minus mv squared over r. Let's see, there's a common mass to both here, so let's go ahead and factor out a common mass. And we have mass times g minus v squared over r. Now we're going to make a little substitution for v squared. Recall how v is equal to the square root of 2, or 2 times the square root of g times the quantity r minus. So if we take this and we square both sides, we get v squared equals 4g times the quantity r minus little r. So we're going to substitute that right there for v squared. So we get the normal force is equal to m times g minus, and then on top we have 4 times g minus big R minus little r, which, I guess for the purposes of what we're doing now, we can go ahead and just distribute that all. So that would be 4g big R minus 4g little r. And that's all over r right down here. Okay, and then now, let's see. We can clean that up a bit. So normal force is equal to, we have G minus, and I'm going to split this up into separate fractions. So 4G big R over little r minus 4G little r over little r, which you can see on the bottom here will cancel. So far we've got normal force equals the quantity of big G, or little g, minus 4G big R over little r minus 4G. And actually, I need to go back and change something, because since we substituted for this, that would be a quantity there, and if you distribute the negative through, that would be a plus, which means that would be a plus. There we go. Almost had an oopsie there. Okay. Normal force. Now we can go ahead and take G plus 4G, and we've got 5G minus what's left over, minus 4G big R over little r. And we can go ahead and factor out a G, since it's common to both parts too. And normal force would be essentially, oops, I forgot to carry the M all the way through there. Let me go back and insert that M there. If you saw that already and are telling me, hey, Mr. Hiller, what are you doing there? So, let's try that again. So we've factored out the M. Let's factor out a G also. And so we've got M times G, and then what's left over would be the 5 minus 4 big R over little r. There we go. That is our value for the normal force. Okay, so if the last step in part A supports engineer B's claim that the planet's diameter height is too large. So if this planet's diameter is way, way too large, then that is going to make this whole value larger, which brings this value to 0. And when you bring the normal force to 0, or even less than 0, then you lose contact with the track. Step 4 supports engineers' claim that let me see, this part right here, we can stop right there. Okay, so if if the value of v squared over r becomes too large, then this value, so if this value here becomes too large, then that will be subtracting more from G, meaning that whole value is much smaller, which means the normal force is smaller. Which could make it too small or possibly negative to make the car fly off the track. Is the ride safe? If Neptune is not safe, what combination of planets would be safe? Okay, so if we take a look at the combination of Jupiter and Neptune, so we're going to take a look at the speeds that were generated, especially the normal force. And let's go ahead and take a look at the equation. So mg, let's examine this equation over here. Okay, so if we look at, let's say, Jupiter and Neptune, so a normal force, don't worry so much about mg, because that's just relating to the weight of the roller coaster. But then we've got 5 minus 4 times 1 over a little r, which is 0.35. Okay, so now if we take 4 divided by 0.35, we actually get about, this part right here would give you about 11.43, which you can see that's going to give you a negative value. So the normal force is less than 0, it's negative. The ride as designed is definitely unsafe. Okay, but now let's see, now Earth being even smaller would be even more unsafe. So no, but could Saturn actually work? Let's find out. So normal force equals mg, and then we're going to go 5 minus 4 times 1, the relative radius of Jupiter, over 0.83. So now if we go 4 divided by 0.83, you get about 4.82, which is fine because all that giving you 4.82, 5 minus 4.82 is a number greater than 1, meaning normal force is now positive, which means the cart stays on the track, which is the most important part. So Saturn could be used instead to make the ride safe.